This topic is finding the rate or time in a word problem on continuous exponential growth or decay. So we have the mass of a radioactive substance following a continuous exponential decay model. So that word continuous is super important. With a decay rate parameter of 6.9% per day. Find the half-life of this substance. That is the time it takes for 1/2 the original amount in a given sample of this substance to decay. Note, this is a continuous exponential decay model. Okay, so that word continuous is so important. They said it 2 times. So let me get rid of that from a different problem. Oh, it's not letting me make it go away totally. Oh, well, it's fine. Okay. So big thing with this whole word, continuous exponential. So if it says continuous exponential growth or decay, then you can use this formula, A equals PE to the RT. A lot of times instead of an A, they used Y. Maybe the P is something different. This is, we first encountered this way back in section 4.2 as the continuous compound interest formula, but it doesn't have to just apply to compound interest. It can apply to any continuous exponential model, growth or decay. And so the P is always going to be your starting amount, and the R is your rate of growth or decay. How did they put it? Decay rate parameter. So they're going to give that to you as some kind of a percent, or if that's what you're supposed to find, then they're going to give you, or that you'll have to type it in as a percentage. So this is whatever that percentage is, but of course you want to use it as a decimal. And you do have to be careful when you have decay. For decay, decay is always going to be negative. The rate is always going to be negative, So they're not going to give you the rate as a negative percentage. You just have to remember that if it's decay, you have to make it negative when you put it into your formula. So then T is your time, and that can be different depending on the situation. It can be days, years, hours, minutes. And then A is the kind of final amount, or the amount after time T. Okay, so let's see. Okay, let's see what all they gave us. So what we can actually put in. So we don't know the amount that we start with, right? It just says the mass has a continuous exponential decay, and decay rate is 6.9%. And then find the half-life. Okay, so let's see. So we know that our R is going to be negative 6.9%, or negative 0.069, right? So always divide by 100. And so this is what we've got. A equals PE to the negative negative 0.069 T. And they said find the half-life. So the half-life is time, right? So the time it takes. So we're supposed to be solving for T, and it would be the time it takes for whatever the starting amount P is for it to become 1/2 P. So instead of the A, let's make this 1/2 P, or P over 2, or 0.5 P, whatever you're comfortable with. And then so we have P times E to the negative 0.069 T. Okay, and so it may seem like we have too many variables, but the first thing we'd want to do to solve this equation is to divide both sides by P, and notice what's going to happen when we do that. The P's are just going to completely cancel out on both sides, and so we're going to be left with just 1/2 equal to E to the negative 0.069 T. And so after you've done like a half-life problem once, you may realize that you can actually just set the equation up to start with as this. 1/2 equals, you could think of the starting amount as just being 1, and then e to the negative, blah, blah, or what, whatever it is, the rate times t. So now, to get at this exponent, we need to get the t in particular, but basically this exponent out of the exponent. To do that, we have to take a log. So we're going to take the natural log, since it's base e, natural log of both sides. So natural log of 1/2 is the same as the natural log of e to the negative 0.069t. But you could actually skip writing this stuff right here, and because the whole point is that we're going to get that exponent out. So we're going to have, sorry, this is getting messy. Let's do a new column. So we're going to have natural log of 1/2, or if you like 0.5, whatever floats your boat, equal to negative 0.069t, because that's the whole point, is that we're doing the log in order to get that exponent. So now we're almost done. We just need to divide by that negative 0.069 on both sides. And then, let's see, I'll have to check and see what they wanted us to round to, but the exact form is natural log of 1/2 over negative 0.069. And it says, oh, round to the nearest hundredth. Okay. So let's see. Let's get this guy going. Okay, so natural log of 1 divided by 2. And then I'm going to click out of that and divide by minus 0.069 equals, okay, 10 point something, and nearest hundredth, so 10.05 once we round. And so that was days, decay rate per day, so not that it matters, so 10.05. So it takes about 10 days for this substance to decay to half its original amount. Okay, check. Yay! So, let's see if we can find one. So we're finding time there. And basically, whenever you're asked to find the half-life, it's always going to be natural log of 1/2 divided by that decay rate. And so, if this were a test question, I'd be fine with you just explaining to me that and writing that out. If there's another version of this where instead of decay, you have growth and it's continuous compound interest, and they ask for the doubling rate, that's always going to be, so it's how long it takes for your money to double. So doubling time, I'm sorry. So that's always natural log of 2. So instead of 1/2, natural log of 2 divided by the interest rate. And that's kind of like a investment. People that do a lot of investments know that little formula. What am I doing? Oh, that's right. I was going to do more practice. I want to see if we can find one where we're finding the rate. Oh, yeah, here we go. Okay. Suppose the number of bacteria in a certain population increases according to a continuous exponential growth model. A sample of 1,700 bacteria selected from this population reached the size of 2,012 bacteria in 5 hours. Find the hourly growth rate parameter. Continuous exponential growth model. Okay, write your answer as a percentage. Do not round, blah, 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 and then round the percentage to the nearest hundredth. So, let's see. Let's get rid of this stuff and switch colors. Hopefully it makes it a little easier to see. Okay. So, we're going to have kind of the same basic formula to start with. A equals P, e to the RT. And so remember, P is what we have to start with, and I think that's going to be 1,700. And then A is 2012, and that's after 5 hours, so t is 5. So that is enough for us to figure out our rate. So let's just put all that in. So 2012 is equal to 1700 e to the r times 5. I'm going to go ahead and just write 5r. So first thing we want to do is get rid of the 1700. We need to get that out of the way. So let's divide by 1700. And we're not supposed to round any intermediate computations, as they said. So we don't want to do too much with that fraction. Let's just see what it is when we put that into the calculator. Okay, so we don't, it looks like they're rounding it off there. We don't want to do this. So we could do something like try and simplify that, but you know what? I'm just not going to worry about it. We'll just deal with writing these numbers over and over. So we now have 2012 over 1700 is equal to e to the 5r. So we need to get that 5r out of this exponent. So we're going to take the log of both sides. So we're going to do natural log since this is an e. So natural log of 2012 over 1700 equals 5r. We could write natural log of e to the 5r, but that simplifies to 5r. That's the whole point. So we're going to divide now both sides by 5. And you can write it like this. I kind of like to put the 1/5 in front, actually, if it's not too big of a number or too crazy of a number that we're dealing with. But yeah, I don't know. It doesn't matter. It's just aesthetics. 2012 over 1700. Okay, and so that's what we're supposed to be figuring out. This is our R, but they want us to put it in as a percentage. So when we type this into the calculator, we're initially going to have, let me get that smaller, we're initially going to have a decimal, and we're still going to want to make it into a percentage. So let's clear this out, maybe make it where you can see the whole calculator. Okay, clear, okay. So 1/5, and then times natural log 2012 divided by 1700, and that's it. Okay, that's what we need to type in. Again, it would be totally fine to do the natural log of all this and then click out of it and do divided by 5. All right, so here's a teeny number, but remember this is the decimal. We need to convert this to a percentage. So do not round at this point. We need to first convert to a percent. So times 100. You can imagine there being a little percent there. Okay, so this is now our percentage. So if we round this to the nearest hundredth, it would be 3.37. And that's the answer they want. So tricky thing there at the end with the rounding.